Hi everyone, Preprocessing here, and welcome to part 2 of my Operating Systems Concepts video series. In this video, I want to talk about how the code you write gets translated into a format that your computer can understand. I'll be using C on macOS, but your results should be similar if you're using any Linux or Unix-based operating system. Also note that some of the things I'll show you in this video will depend on what processor you have in your computer. In my case, I'm using an Intel x86 processor, so the assembly code that you'll see later in this video will be x86 instructions. Alright, here I'm in a new directory with a C program called fib.c, and if I open it up in Vim, it's just a C program that prints out Fibonacci numbers up to 100. Now let's try compiling and running this, so I'll do gcc-o fib.c. This produces the executable called fib, and if I run fib, you'll see it prints out the Fibonacci numbers up to 89, which is the last Fibonacci number before 100. Alright, the rest of the video is going to be dedicated to explaining what just happened, how the C program we wrote got converted into a format that our computer was able to run and print output to the console. So let me open fib back up again. Now even though this is a simple C program, your computer can't directly run this code. This is a format that's very human readable, if you will, but it's not something that your computer can just directly start executing. There are several steps that need to happen before this code can actually be directly executed by your processor, and we'll cover some of those steps in this video. Before even beginning to compile any code into a machine-readable format, your compiler performs a preprocessing step. This step expands certain macros in the C language into more simple forms. Here we just have one preprocessor directive, the include statement. This just says copy the contents of standard.io.h and put the result at the top of this file. Let's see how that actually looks. So I'm going to quit out of this, and although we can generate the fib executable in one step by just typing gcc-o fib.c, I want to break it down into what steps GCC performs internally. The first step, like I mentioned, is the preprocessing step. And if we want, we can tell GCC to only perform the preprocessing step. The way we can do that is by using the -e flag. So I'll say gcc-e fib.c-o fib.i. It's common practice to suffix your preprocessed files with a .i extension. Now if I look at fib.i, you'll see it's still, there's a bunch of stuff at the top, but it's still, it's still C code. It's still, for the most part, human readable. And if I look at the bottom, here's our main program that we wrote earlier. So what happened is just that the include standard.io.h just got replaced with the contents of standard.io.h itself. And that's what this is. Of course, if you're on a different platform, things will look different. You can see I have plenty of references to macOS specific things, but the idea is the same. The include director will just replace that line with the contents of the file you included. And then at the bottom we have our code. Okay, that's the preprocessing step. The next thing your compiler does is perform the compilation step. It might seem like your compiler would only do the compilation step, but actually GCC does a little bit more than that. In the compilation step, your C code gets converted to an entirely different language. It gets converted into assembly code. Now, assembly code is still sort of human readable, but it's much closer to the format that your computer actually understands. So let's look at what happens when I try to run GCC and tell it to perform the compilation step. Passing the -s flag to GCC, I'll tell it to do the compilation step. And then I'll give it fib.c. Fib.c. And now if I ls, you'll see there's a new file called fib.s. Alright, let's open up fib.s. Okay, so this now looks much different from our C program. You can see even if I go to the bottom of the file, there's no while loop, there's no main method. This format is x86 assembly code. If you're on a computer that doesn't use an x86 processor, your assembly instructions will probably look different. Now, if you're looking at x86 for the first time, all of this might look like gibberish, but it's still sort of human readable. You can see we have things like subq or comparison. We have a move instruction. I won't try to cover all of x86 instructions in this video, but let me try to give you a sense of how these instructions still represent our main program, which printed out Fibonacci numbers. So when our program begins, we'll jump to the main label, and we'll start running instructions below the main label. So here we have some instructions. These are kind of hard to interpret directly, but we have this other label called LBB01. This is just an auto-generated label. It doesn't correspond directly to any function. But from reading the assembly code, I can kind of tell that this label marks the beginning of the while loop. So you see that we have a LBB01 here, and then later on we have a JMP, or jump instruction, that says jump to LBB01. So that's kind of a loop, right? Because we start from main, we go through a bunch of these instructions, we reach this label, which I think is the start of the while loop, and then we execute some more instructions, and then later we jump back to the start of the while loop, right? We jump back here, and then we're going to execute the same instructions over and over again, right? We reach the bottom of the loop, we jump back to the top, and so on. So now you might ask, okay, well, this looks like a loop, but how do we get out of this loop? And the answer is over here. See this LBB03 label? That's at the end of our loop, right? It's after the jump back to the start of the loop instruction. So if we can get over here, we'd be out of the loop. So where do I see LBB03? Well, that's over here. So this CMPL instruction, it performs a comparison. You also see the number 100 here, right? So what this is actually saying is it's checking if our variable is less than 100. Now this encodes where the variable is stored in memory. If you haven't seen the syntax, this will be pretty confusing, but just trust me that this represents where our variable is stored in memory. So we're taking the value in memory at this location, and we're comparing it to 100. Now this JGE, this is like a jump greater than or equal to instruction. This says if the previous comparison said the comparison was a greater than or equal to, then we'll jump to this label. Let me open up the code on the side to explain this. So our while loop was while b is less than 100. And so we want to keep executing the loop as long as b is less than 100. So when do we want to exit the loop? That's when b is greater than or equal to 100. So what this instruction does is it compares our variable b to the constant 100. And then, if b was greater than or equal to 100, we jump to the LBB03 label, which is at the end of the while loop. So that's how we exit the loop. So hopefully that kind of makes sense. Of course, don't worry, I don't expect you to be able to look at these instructions and know everything that's going on. But hopefully this gives you a sense of how these assembly instructions still represent our Fibonacci program. Okay, now let's move on to the next step. The next step is to do something called assembling. We've generated assembly code in the compilation step, and now we need to assemble the assembly code into machine code. Machine code is one level below assembly code, and it represents a format that your computer can actually understand. Alright, so let's try to invoke GCC and tell it to assemble the code. The way I can tell GCC to perform the assembly step is by saying gcc-c fib.s. So this assembles the assembly code we wrote earlier and generates a new fib.o object file. I can try to open this file. I can try to open up this file to see what's in it. So let me do that, fib.o. And you'll see I get a whole bunch of garbage. That's because the .o file, which is an object file, is not human readable. It's in binary. So instead, let's look at what's actually in the file by printing out the bytes in the file. I'll do that using xxd fib.o. And you can see I get a whole bunch of stuff here. There are some human readable strings like text, but really there's not too much to be learned by looking at this. So instead of trying to understand the file by looking at the raw bytes, let's use objdump. So I'm going to objdump-d fib.o. Now you can see I get some nicer looking up. So if I scroll up, you'll see there's a main label here. This again corresponds to the main function we wrote earlier. And you can see that it's generated some instructions that should look familiar, right? We have this jump, we have the comparison, we have the jump greater than or equal to instruction we saw earlier. And so what objdump is doing is it's actually disassembling the code. So we assemble the code, and then objdump is disassembling it and getting back the instructions in assembly format. So over here is the disassembled code, and over here is the raw hex values. So you can see that at offset 0, I have the single byte 55 in hex, and at byte offset 1, I have this sequence of hex bytes, and that corresponds to this move q instruction. And at the 4th offset, I have this sequence of 4 bytes, and then you can see at the 8th offset, I have another sequence of bytes, and so on and so forth. And so what this objdump is telling me is that these bytes correspond to this instruction. So anyways, the point is that the object file is just a machine-readable version of the assembly code, and we can get back the assembly code by running objdump. But of course, your computer won't directly run the assembly. It runs the object file code. The next step is called linking. Linking basically says, take a bunch of object files and link them together. If you remember, our code called printf to print out Fibonacci numbers, and so we would at least need to link in the object file containing the printf function definition. When you run the linking step, a bunch of object files get linked together. This way, functions in one object file can call functions that are located in another object file. Linking is the last step that GCC performs, and so we can run GCC from start to finish by typing gcc-o fib.c. This just says preprocess the file, compile it, assemble it, and link it, and store the output in a file called fib. So if I run that, you'll see now I get a fib executable. To run this, I can type /fib, and it prints out my Fibonacci numbers as I wanted. So there's one last step in this process that's not performed by GCC, but instead by your operating system, and that is the loading phase. The loading phase is where an executable on disk, such as this fib file, gets loaded into your computer's memory so that it can actually be run. So when I type /fib, my operating system creates a new process, loads in the machine code in fib, and starts running it on my processor. And then my processor will execute the instructions that you saw in assembly and produce this output. Okay, phew, that was a lot. There's a mnemonic that people often use to remember the stages in this process, and that mnemonic is CALL, C-A-L-L, which stands for compiling, assembling, linking, and loading. It misses out on the preprocessing step, but that's kind of applicable only to C, and not really to other programming languages. Alright, that's it for this really quick overview of how programs in C get converted into binaries that your computer can directly run. There's a ton more to know about this process, and you can take courses or read books about how compilers work. You can learn much more about how the operating system actually loads your executable into memory, and so much more. But hopefully this gives you insight into what each process does, what its inputs and outputs are, and how it plays a greater role in the overall process. Hopefully you found this video informative. If you have any questions or comments, please leave them in the comment section down below. Thanks, and see you next time.